All right, yeah. You guys missed some good stuff at home. Maybe. All right. So, so an aromatic molecule is a lot more stable than the Lewis structure suggests. Right? If you look at the benzene, cyclohexene, we get a delta H of minus 120 for hydrogenating the double bond. For the cyclohexenes, sorry, the hexadienes, you'd expect that to double to 240. If the double bonds aren't conjugated, it's really close. If they are conjugated, you don't get quite as much stabilization. If the molecule's aromatic, you get way less stabilization. All right? So benzene is not just a little more stable than you'd expect, it's a lot more stable. So that's what aromaticity means. Benzene doesn't do any of the, right? So that stability basically means, right, if I treat benzene with bromine, there's no reaction. If I take styrene, you guys have heard the word styrene before. If I take styrene and treat it with bromine, it stops with addition to, right, the two BRs add to the alkene, not the benzene. The reason why aromatic molecules are more stable than you would expect is, again, a molecular orbital argument. Right? If you think about the molecular orbital of benzene, because it's cyclic, right? Because it's a cyclic molecule, those 6 p orbitals all have a bonding interaction with each other. That's a bond order of 6. That is super stable. It actually turns out I'm just going to draw this in here. You can find this in the book. Again, I don't expect you guys to memorize these. How we get the molecular orbitals, again, is mathematics, but we're not going to do. But basically what happens, we have 6 pi electrons, right? Benzene's got 1, 2, 3 pi bonds. 6 pi electrons, two electrons in each pi bond. 2 of those electrons are in an orbital that has a bond order of 6. The other 4 are in 2 equally stable orbitals that have a bond order of 2. Right, so the bond order of the HOMO, again, you've got highest occupied molecular orbital. There are 2 of them. In all the other alkenes, that highest, the HOMO of the polyenes, the non-aromatic conjugated alkenes, that top, the highest occupied molecular orbital has a bond order of 1. It's like a pi bond. It's like an alkene. Right? So these alkenes basically are as reactive as an alkene. The other 4 are more stable, so more stable. But because of the cyclic nature of benzene, these 2 HOMOs wind up bond order of 2. Okay, so benzene is not as reactive. Also, the lowest unoccupied molecular orbital has a bond order of -2. So putting an electron in is harder than just an alkene. Point is, benzene and other aromatic molecules are quite a bit more stable than you expect, just based on the Lewis structure. I'm going to show you some examples where that does not mean they're more stable. Okay, it just means they're more stable than you expect. flying down the board today. Okay, so we got rules for is a molecule aromatic or not. Like I said, this would be quite, you guys might think this is challenging anyway, but it would be a really challenging class if you had to solve differential equations for every molecule. And in fact, that's what they thought in the, so the quantum mechanics folks in the 20s figured out aromaticity about the same time as the organic chemists were sort of coming up with an empirical way to figure out aromaticity. Organic chemists didn't want to solve, we didn't want to solve differential equations for every molecule. So, the first rule is you've got to have a cyclic set of p orbitals. And then it's got to be planar. Okay, so this is not maybe that easy to see, but come all the way back over here to just what a pi bond is. All right, I've got two p orbitals that come together. Let's see if I can put this on camera. All right, so a pi bond, if you imagine my markers being pi bonds, right? They've got to come together like this and overlap, right? Right? Not good. Okay, two p orbitals have to come together like this. That means they have to be in the same plane. If one of these is twisted, when they come together, you don't get a pi bond. And you might think, well, come on. If they can be planar, they'll be planar. And that's actually the answer. How do you know if it's planar? If they can be planar, they will be planar, right? So if I'm taking these p orbitals and putting them together, they will come together to overlap if they can. Remember, all these molecules are trying to make themselves as stable as possible. And they're not sentient organisms like I talk about, all right? So they want to come together planar. It would have to be something steric that would make them not be planar. So if there's some reason they can't be planar, then maybe they're not planar. But otherwise they will be. And then finally, and this is the one that always kind of throws people. I don't want to tell you that this is going to be the thing that confuses you, but it is. All right. To be aromatic, that cyclic set of orbitals has to contain 4n plus 2 electrons. N is any integer. Integer. What's an integer? Whole number. Pi. Is pi an integer? No, it's 3.14 or 15. Anybody got more than that? Okay, some of you can do more. My brain's going. I sometimes forget my wife's name, that sort of thing. Sorry, she forgets mine too. So, 0, 1, 2, 3, 4, 5, those are integers. Now, here's the thing. Do not imagine you know the integer first. Count the electrons before you do anything. All right? So we look at benzene. How many pi electrons are in benzene? 6. Does 6 equal 4n plus 2 where n's an integer?
Yes.
It does. N is 1. 4 times 1 is 4, plus 2 is 6. You are asking yourself if the number of pi electrons equals this. You're not trying to imagine going into it that n is something. Okay? So if that's true, if you have 4n plus 2 electrons in a planar cyclic set of p orbitals, that molecule is aromatic. I'll give you a hint. Any molecule with a benzene, so that's toluene. Toluene is an aromatic molecule. Some molecules you've seen before. Benzoic acid is an aromatic molecule. All right, they have a benzene in them. Benzene is an aromatic. So you should get, exam 1 is going to have a question where I've got a whole bunch of structures and you have to tell me if they're aromatic or not. If it's got a benzene in it, it's aromatic. But make sure it's a benzene and not a cyclohexadiene. or something like that. Okay, so let's do a more challenging one than that. I'll draw 3 structures. You tell me which, if any, are aromatic. So I'll give these numbers. I'll give them letters. How about that? A, B, C. So think about them for a couple of seconds. How about A? So does A have a cyclic set of pi or p orbitals? What's the hybridization of that carbon? sp2. Hybridization of that carbon. sp2. Hybridization of that carbon. sp3. Does an sp3 atom have a p orbital on it? No. So this is not cyclic. All right, so A, cyclopropene, has a pi bond. It's a really strained pi bond. You guys remember bond or ring strain, right? Bond angle here is 60 degrees because it's it's a triangle. It wants to be 120. 60 is not 120, so that's really strained. But because that carbon interrupts the cyclic system, that carbon makes the molecule not aromatic. Right? It's not aromatic, it's not anti-aromatic. I haven't talked about anti-aromatic yet. But all right. Does B have a cyclic set of p orbitals? So if you're looking at what I'm trying to do, are we still on? We're still on. What's the hybridization of this carbon?
sp2.
sp2, there.
sp2.
sp2. Carbocations are sp2. An sp2 carbon has one p orbital. All right, so this compound B has a cyclic set of p orbitals. It's a cyclic pi system. Every atom in the ring is engaged in the pi system. All right, and it can be planar. There's nothing sterically preventing that molecule from being planar. So now rule 3. How many pi electrons are in compound B? 4. Does 4 fit 4n plus 2? It does not. It fits 4. N would have to be a half, right? A half is not an integer. So 4 pi electrons. So 4 pi electrons, I'm not going to make a huge deal out of this. So that fits 4n, where n is an integer. Turns out that molecule is anti-aromatic. What do you suppose anti-aromatic means? It means
It fits the first 2 rules, but not the third.
No, it means, so if you look at aromatic, what aromatic means is it's more stable than you would expect it to be. Anti-aromatic means it's less stable than you'd expect it to be. That looks like, that's a delocalized cation. Before today, you guys would probably tell me, yeah, that's a pretty good cation. You can draw resonance structures. That'll do SN1 and E1. That molecule, if I have a chloride here, that chloride will not leave. Because then it would make an anti-aromatic molecule that's quite unstable. All right, so what about C? I've got you all turned around. Nobody wants to say what they think. Yeah.
It's not a cyclic set.
So that's, again, this is, I hate to do this. Because like I tell you guys in Orgo 1, I talk about carbanions a fair amount. The hybridization of most carbanions is sp3. Don't write that down. All right. Hybridization is this weird thing that, again, is organic chemists trying not to do differential equations. We come up with this really kludgy hybridization system. It works remarkably well to describe the chemistry of carbon compounds. All right? I don't want you to forget about hybridization. But it's an approximation. And it fails, so you're absolutely right. That you would think is an sp3 carbon. But here's the thing about hybridization. If a carbon can, if the two orbitals can planarize, they will. So what happens here is there's one hydrogen here and a lone pair. Right? So there's a lone pair of electrons. That lone pair of electrons, the orbital it's in, which you'd expect to be sp3, will planarize with the others and participate in the cyclic system. Okay, so if we look at this on edge, I'm going to write the letter C here for the carbanion. That carbanion, instead of being an sp3 orbital with a lone pair, with a pair of electrons, planarizes into a p orbital, and then you've got the pi bonds. Right? Each of these double bonds, then each atom contributes one electron. The total is 6. You get 2 electrons from the negative carbon. You get 2 electrons from each of the 2 double bonds. So this turns out to have 6 pi electrons. All 5 carbons are participating. That's an aromatic molecule. It's an aromatic ion. So before I drew this, would you expect that anion to be really stable? Anyone? Negatively charged carbons? Yeah, no, you wouldn't. Negatively charged carbons are pretty unstable. We're going to see a lot of them this semester, but they're pretty reactive. Again, the point is that underlined bit is important, right? Aromatic molecules are more stable than Lewis structure suggests. It doesn't mean they're stable. This carbanion is still a really strong base. If it touches water, it reacts. If it sits in the air, it reacts. But I can make it. I can make this anion a lot easier than I can make that cation, even though the chemistry we've shown you guys so far would suggest the opposite. Okay? I'm going to draw 2 other molecules, talk about them, and then we'll move on. We'll come back. I'll assign some. All right, consider these 2 molecules. Are they aromatic or not? And I swear I'm not trying to trick you guys. They just are a little tricky. All right, how many people think both molecules are aromatic? How many people think one of the 2 is? How many people think neither are? They say young people don't vote. You guys should vote, by the way. Not really an expert in this field, but all right. These are both aromatic molecules. Groans. Molecule on the right is called pyridine. Pyridine is an excellent example of an aromatic molecule that does not smell so nice. Pyridine stinks really bad. Compounds with nitrogen and sulfur tend to smell bad. And the reason we think is it's evolutionary, right? We're made up of proteins. There's a lot of nitrogen in them. There's some sulfur in them. Once an organism stops being alive, the molecules in that organism break down, and you get these free amines, you get these free thiols, and we smell that as death. Pyridine smells really bad. It's also a mild carcinogen and creates something called testicular atrophy. Yeah, okay, all the guys made a face. That was bad. Don't get near pyridine if you can avoid it. It's a really good solvent though. Thiophene is another aromatic molecule. You find it in crude petroleum. It's a really important. There's quite a bit of sulfur in crude petroleum, crude natural gas. That has to be filtered out, right? You've probably heard of acid rain. We used to not desulfurize our fuels. We would burn it, and you get all this sulfur dioxide in the air that would react with water and create sulfuric acid. Thiophene was part of that. So anyway, these are molecules you've seen now. So here's the thing. Why are they aromatic? This lone pair here, if you said pyridine's not aromatic, maybe, I'm going to surmise that it's because you counted 8 electrons. I put this lone pair here. I said I wasn't trying to trick you, but I put that lone pair there to trick you. Right? The only thing that counts are the 3 pi bonds. This lone pair is actually, right, it's in the plane of the board. The p orbitals are sort of out and back of the board. The lone pair is down. That lone pair is not conjugated with, it's not part of the cyclic set of p orbitals. So if you see a 6-membered ring like this that's got 3 alternating double bonds, that's going to be like a benzene. So pyridine's aromatic basically for the same reason that benzene is. Thiophene is just like, again, I drew both lone pairs, and maybe you counted 8, but you can only count one of those lone pairs. So what happens is, like that earlier example, right, we did cyclopentadiene anion. That lone pair hybridizes to be planar. Okay, so here's the 2 pi bonds in thiophene, and then the sulfur is here. Sulfur can't put 2 orbitals in the same place, right? So it can't have 4 electrons all part of the system. It puts 1 orbital there, and then 1 orbital is out here. Basically, that sulfur hybridizes itself to be sp2. It's got 1 p orbital that participates in the cyclic system. The other lone pair sticks out here. So there's 6 pi electrons. All right. Yeah?
So does that third rule just mean that there needs to be like an odd set of pi bonds?
Basically, yeah. Or 2 in a lone pair. If a lone pair can, if a lone pair is participating, then it does. The other thing, like, there's some crazy ones. I'm going to assign some in the book that you'll see, like cyclopropene cation is actually aromatic. And again, that doesn't mean it's stable. It's got fallacious ring strain, it's got positive charge, but it's got a cyclic set of 3p orbitals with 2 electrons in it, right? N is 0. You can get some other ones, so we can do, drawing a 7-membered ring is sometimes hard. Same thing with cycloheptatriene cation, cyclic set of p orbitals, 6 electrons. So that's aromatic. Really though, fundamentally, like, there are going to be some problems and there's some tricky ones, but here's really what you need to know. Like, if you want to memorize something. I don't like memorization. And actually, you can have any of these. If you have, I shouldn't even do that. Pretty much, if you have a 6-membered ring that's got all 3 alternating pi bonds, that's aromatic. Whatever the atoms are, right? There's some crazy examples. Like that is a known molecule, that's aromatic. And again, aromaticity doesn't mean it's unreacted. It means it's more stable than you would expect. Lower in energy than you'd expect. Okay. X here, X can be, if X has a lone pair on it, so that X can be a carbon, it can be a sulfur, it can be an oxygen, it can be a nitrogen, it can be a phosphorus. Right? If that X has a lone pair, it's going to be an aromatic molecule. And you see a fair amount of these in nature. If you go look at natural products, you see a lot of benzenes. You see a lot of heteroaromatics that have a nitrogen in them. You see a lot of 5-membered rings that have an aromatic in them. You guys have seen, if you know your amino acids, this is a side chain. All right, there's amino acid off that. And those are 2 fused aromatic rings. There's a benzene and a imidazole ring. Not an imidazole, pearl. Anyway. I'm going to move on to put up the Diels-Alder. Yeah, sorry.
Sorry, if there's 2 lone pairs like that, do you always assume that it hybridizes sp2? Like,
Yeah, so one of them can. Right? So the second, if it's going to hybridize sp2, it can't put a second lone pair in the system. Right? You can't have 2 orbitals in the same place. So like I said, I'll assign some of these where you like the book is like, tell me which molecules are aromatic, tell me which are anti-aromatic. Work on those. We'll do a few more on Monday when you come back in. And I'm going to hit pause unless I've already